everybody, this is Dr. Nigro with a Chem Calculation Screencast. This screencast is going to expand on our understanding of how to determine the empirical and molecular formulas of a compound by including combustion analysis of hydrocarbons. All right, so combustion analysis is a type of investigation into structure and formula that utilizes a combustion reaction. So we take some sort of hydrocarbon that contains carbon and hydrogen at the very least, and then combust it in the presence of O2, forming carbon dioxide and water. All right, so for a general reaction, we would have some carbon and hydrogen compound in the presence of oxygen gas, and when that combusts, we're going to form carbon dioxide gas and water vapor. All right, now, if you look at this reaction, you'll see that for the carbon that forms, all of it has to end up in that CO2. All right, so that means that if we know the amount of carbon dioxide that forms from this reaction, then we can determine the amount of carbon that must have been in our original compound. All right, by the same token, all of the hydrogen that was in that compound must show up in that water molecule. So if we know the amount of water that is produced by this reaction, we can determine the amount of hydrogen that is produced. Now, how does this happen? Well, there's a furnace and it's a combustion analysis apparatus. And what really happens is you add oxygen in to your sample in this furnace, and as the gases are produced, they move down the apparatus into two additional chambers. The first chamber contains something like magnesium perchlorate, which absorbs water vapor. So as the water particles move over this substance, they get absorbed into that substance. And the mass of that magnesium perchlorate before it's exposed to the water vapor and after lets us determine the amount of water that was produced. By the same token, if we want to determine the absorption of CO2, the amount of CO2, we use something like sodium hydroxide, which is a strong base. It's going to interact with that carbon dioxide as it moves past, absorbing that. So we then absorb the CO2, and again, we take the difference in mass before the exposure to CO2 and after, and that gives us the amount of carbon dioxide. All right. What do we do with that once we know the amount of water and the amount of carbon dioxide? Well, if you remember, in an earlier screencast, I have my jingle, which is percent to mass to moles, divide by smallest, multiply until whole. All right, and we're going to keep some of that in determination of the empirical formula. We're not going to have percent to mass because these problems are not going to include percentages of these elements. Instead, we're going to say mass of compound to moles of element. All right, so that's going to be our first step. All right. Oh, actually, you know what? Let me change that. Let's make that 2 steps. All right. So we'll say mass of compound, and we're going to go to moles of element. All right. And once we have all the moles of our element, we're going to again divide by the smallest. And if needed, we'll multiply until whole. All right, so this step here, all right, this is where the amounts of carbon dioxide and water are going to come into play. All right, it's going to be a 2-step mole conversion problem. We're going to take the mass of the compound first. We're going to do a little stop at moles of that compound. All right, which means we're going to need its molar mass, and then we can go to moles of element, and we're going to use that mole ratio for that. All right, so for example, all right, let's say, just for funsies, let's say in this reaction we produced or measured that we absorbed 5.25 grams of CO2. All right, well, what I really want to know are how many moles of carbon are present. All right, now I can't go directly between those two, so I'm going to take those grams of CO2 and I'm going to convert that into moles of CO2. So I'll need the molar mass of carbon dioxide. And then once I know moles, then I can convert to moles of carbon using the mole ratio. All right, now remember, this is looking at an element within a compound. All right, so that mole ratio, you're going to be looking at the subscripts of the elements to make that jump. All right, by the same token, maybe I have 5.25 grams of water instead. All right, and to determine the moles of hydrogen, I'm going to do a similar two-step problem. I'll convert to moles of H2O, and again, molar mass, but this time of water, and then I can convert to moles of hydrogen, again with that mole ratio, and we'll be using the subscripts. All right, so that's going to be our general process to determine the amount of carbon and hydrogen. But what if we have a compound like this, where we have another element? All right, so in this case, oxygen, but what if it's nitrogen or chlorine? There's all kinds of elements that can interact with these hydrocarbons. All right, it's going to depend on the problem. All right, if you have something like this, just keep in mind that the total mass of your compound has to be equal to the mass of the carbon plus the mass of the hydrogen plus the mass of the oxygen. All right, so if I can utilize the moles of carbon, I can convert that to mass of carbon. All right, I could do the same thing if I calculate moles of hydrogen. I can convert that to mass of hydrogen. All right, and the problem should give me the total mass. So if I have the total mass in two of the elements, then I can find the moles of oxygen. And then from there, mass to moles, and then I look at those three element moles and divide by smallest and multiply until whole. All right, so that is another type of problem we run into, and I'm going to do an example of one of those down below. All right, the last thing to remember is if you have an empirical formula and you're trying to determine the molecular formula, you're going to need the molar mass of that empirical formula, and you're going to need the molar mass of that molecular formula. And the division of those two, the molar mass of the larger, which is the molecular formula, divided by the smaller, the empirical formula, is going to give us some whole number ratio or whole number factor. And then we're just going to multiply all of those subscripts by that value. So let's say, for example, we had an empirical formula of C2H5, all right, and we found that this factor was 2. Well, then our molecular formula must be C4H10. All right, so don't forget that step. If it asks for the molecular formula, you got to do this last step. All right, so let's try a couple. I've got 3 here. They're different, all right, but they're going to build as we go through them. They'll get a little more complicated as we move through them. All right, so we have a hydrocarbon fuel that's fully combusted with 18.214 grams of oxygen to yield 23.18 grams of CO2 and 4.729 grams of water. What is the molecular formula if the molecular mass is 78.12? All right, so we've got some hydrocarbon in the presence of oxygen gas giving us CO2 and H2O. All right, now the amount of oxygen is irrelevant because it's not in our original hydrocarbon, so we don't really care. We just know that we have enough of it to fully combust that CH compound. So we don't have any excess CH compound, all right? We do produce 23.118 grams of carbon dioxide and 4.729 grams of water. All right, as we saw before, all of the carbon is in that 23.118 grams, and all of the hydrogen is in that water. So we're going to convert grams of CO2 to moles of carbon, and then we're going to do grams of water to moles of hydrogen. And then we'll divide by smallest and multiply to a whole if needed. All right, so this is just mole conversions. So 23.118 grams of CO2. 1 mole of carbon dioxide has a molar mass of 44.02 grams. If you've done these problems as many times as I have, you will just know what the molar mass of carbon dioxide is. All right, and then for 1 mole of CO2 molecules, I have 1 mole of carbon atoms. So that's our mole ratio step. We check our moles of CO2 cancel, grams cancel, and we're left with 0.525 moles of carbon. Right, actually, I should have a couple more digits there, but that'll be okay for right now. All right, now we're going to do the same thing with water, 4.729 grams of H2O. 1 mole of H2O has a mass of 18.02 grams. All right, and then 1 molecule, or 1 mole's worth of H2O molecules contain 2 moles of hydrogen atoms, and that is that subscript, that 2 that's going with that hydrogen. All right, we multiply that out and we get 0.525. Well, look at that. All right, then we compare the two. They are the same. So we divide by 525 and we get a 1 for the carbon, divide by 0.525, 1 for hydrogen. So our empirical formula is CH. All right, now the molar mass of CH is 1 carbon plus a hydrogen, 13.02 grams per mole. All right, so to determine the molecular formula, I'm going to take the molar mass of that formula and divide it by the molar mass of my empirical formula. All right, so the problem told me the molecule had a mass of 78.12 grams per mole. I'm going to divide that by 13.02 grams per mole, and I'm going to get a 6. So that means my molecular formula must be C6H6, also known as benzene. Okay, so again, pretty straightforward. All the carbon's in the CO2, so we use the mass of CO2 to convert to moles of carbon. All of the hydrogen is in the water, so we move the mass of water to moles of hydrogen. And then we just repeat what we did with empirical molecular formula calculation. Divide by the smallest. In this case, we were all set. All right, so let's look at this next one. All right, 12.915 grams of a biochemical substance containing only carbon, hydrogen, and oxygen was burned in an atmosphere of excess oxygen. So all that's telling us is we had plenty of oxygen to burn up all of our biochemical substance. Subsequent analysis of the gaseous result yielded 18.942 grams of carbon dioxide, 7.749 grams of water. If the molecule has a molar mass of 120.12, determine the molecular formula. All right, so the end is going to be similar to what we just did. The difference here is we also have oxygen. All right, so we've got some compounds, C, H, and now we've got O. All right, so we don't know anything about where that oxygen is in terms of our products. You can get there. It's very complicated, particularly if you have excess oxygen for our reactant side. So instead, you're better off going after the mass. So the mass total of our substance has to be equal to the mass of the carbon plus the mass of the hydrogen plus the mass of the oxygen. So as we're working through carbon dioxide and water, we're going to find these two values. And then the problem gave us the total. So that's going to leave us a single unknown, which we will use at the end. All right, but before we can do the oxygen, we got to deal with carbon and hydrogen. All right, so we'll start with carbon. We've got 18.942 grams of CO2. I know that 1 mole of CO2 has a mass of 44.02 grams. All right, and for the mole ratio step, I know that 1 mole's worth of CO2 molecules contains 1 mole's worth of carbon atoms. So I multiply that out, and I get 0.430 for my moles of carbon. All right, now we're going to look at hydrogen. All right, same thing, 7.749 grams of water. Convert that to moles using the molar mass. 1 mole of water has a molar mass of 18.02 grams. And then our mole ratio step, 1 mole of water molecules contains 2 moles of hydrogen atoms. All right, multiply that out, and we get 0.860 for our moles of hydrogen. All right, now that's great. We've got the moles of 2 of our 3 elements, but we need the third. All right, and to do that, I need the mass of carbon and the mass of hydrogen. So what I'm going to do is an extra step where I use the molar mass of carbon. So 1 mole of carbon atoms has a mass of 12.01 grams. All right, and that's going to give me the mass of carbon within my CXHYOZ compound. All right, I'm going to do the same thing with my hydrogen. I'm going to multiply it by its molar mass, 1.01 grams of hydrogen atoms for every 1 mole of hydrogen atoms, and I'm going to get 0.868 for those. Oopsie, sorry, that should be grams. Sometimes my pen wants to erase on its own, and sometimes it doesn't. All right, so that's going to be grams. All right, so what am I going to do with that? Well, we're going to go back to my mass total. All right, so the total mass of my compound is 12.915 grams, and that's equal to the mass of carbon, which is 5.16 grams, plus the mass of hydrogen, which is 0.868 grams, and then the mass of oxygen, which I do not know. All right, so I add those two together, then subtract it from my 12.15, and I find that the mass of oxygen within this sample is 6.89 grams. All right, so that's my mass of oxygen. Now I'm going to convert that into moles. So 1 mole of oxygen atoms has a mass of 16 grams. So it's going to cancel. And I'm going to be left with 0.430 moles of oxygen. Well, look at that. How convenient. All right, so I look at these three values and I divide by the smallest. All right, two of them are the same, so I'm going to divide by 0.430. So I must have one carbon atom, 0.430, two hydrogen atoms, and 0.430, one oxygen atom. Oh, I'm running out of room. We'll do the best we can. So my empirical formula is CH2O, and this has a molar mass of, if I add that up, 30.03 grams per mole. All right. If I want to determine the molecular formula, its molar mass was given in the problem as 120.12. All right, so if I divide those two, I'm going to get a whole number of 4. Sorry, I'm running out of room, or I would show you that calculation. All right, that 4 is coming from the molar mass of 120.12 divided by the 30.03. All right, so that means this molecular formula must be C4H8O4. Okay, so that's an example of one of these combustion analysis problems where you have oxygen present. All right, but there are other combustion reactions that we can run where there might be other elements present. All right, and that's what this last problem is going to look at. So an unknown compound contains only carbon, hydrogen, and nitrogen. During the combustion analysis of 11.04 grams of this compound, 12.923 grams of CO2, and 6.608 grams of water were measured. In a separate reaction, treatment of 5.32 grams of the compound with H2 gas resulted in all of the nitrogen being converted to 1.209 grams of NH3. All right, what is the empirical formula? All right, so we really have two reactions. All right, so reaction number 1, all right, we've got 11.014 grams of our compound, and that's going to produce 12.923 grams of carbon dioxide and 6.608 grams of water. Now, of course, there are other products here, but these are the only two that we're given information about. All right, then a second reaction is run. This one doesn't start with the same amount. It starts with 5.325 grams of our compound, and it's reacted differently. Instead, it reacts with hydrogen, and that pushes all of the nitrogen out of our compound into ammonia, where we produce 1.209 grams of ammonia. All right, so this is kind of our situation. All right, so we're going to do the same thing that we did before with the carbon and the hydrogen using the CO2 and H2O. So let's start there. All right, so again, 12.923 grams of CO2. 1 mole of CO2 has a molar mass of 44.02. You can see why I know that molar mass by now. And then 1 mole of CO2 molecules contains 1 mole's worth of carbon atoms. So we multiply that out. We get 0.29. Oh, we got 5 digits here. Whoops. 29357. That's in moles of carbon. All right, so there's the carbon. All right, hydrogen. All right, 6.608 grams of water. All right, then we've got 1 mole of water molecules have a mass of 18.02. That's in grams. And then for our mole ratio step, 1 mole of water molecules contains 2 moles worth of hydrogen atoms. All right, again, we multiply that out. We get 0.7334 moles of hydrogen. All right, now, could we take these, convert them to grams, and then subtract that from our total to find the nitrogen? Yes, because in this particular instance, they've given us that amount. However, we also could use that ammonia value, all right, because that's another way to determine the amount of nitrogen, all right? So if we start with 5.325 grams of the compound, we produce 1.209 grams of ammonia. All right, and all of the nitrogen from our compound has ended up in that ammonia. All right, so we know that 1 mole of ammonia has a molar mass of 17.04 grams. All right, and then we know that 1 mole of ammonia molecules contains 1 mole of nitrogen atoms. So you can see it's very similar to what we did before, except we're working with ammonia. All right, so we multiply this out and we get 0.07095, and that's moles of nitrogen. The problem is this is in 5.325 grams of our compound, not 11.014 grams. All right, so we can't compare this value, this value right here, with our values for carbon and hydrogen because we didn't start with the same amount of our starting material. All right, but that's okay. We just need to scale it up. All right, so if I am going to get 0.07095 moles of nitrogen if I burn 5.325 grams of the compound, then I should be able to figure out how many moles of nitrogen I would get if I started with more, 11.014 grams of that compound. If I do that math, I find that I have 0.1468 moles of nitrogen. Now that number is comparable to the other two. All right, so if you ever are asked to find the amount of a third element using a different starting amount than your CO2 and H2O, you have to scale it up. All right, so just be careful. Just watch out for those. All right, now let's do our divide by smallest. Well, nitrogen is the smallest, so 0.1468. So we're going to have 1 atom of nitrogen. We go back to carbon, divide it by 1468, and we find that we have 2 atoms of carbon, and then we divide our hydrogen value, 0.468, and we have 5. All right, so our empirical formula is C2H5N. And because the problem does not give us any information about a molecular mass, we're all done. We have calculated that empirical formula. Okay, so again, the combustion analysis part just makes you utilize combustion products to determine the moles of your carbon and hydrogen. And then either by subtraction to figure out the third element or a scale up process like I showed you here if you have an extra reaction. Okay? All right, make sure you practice.